We're looking at the second practice test here of the advanced functions unit. We're going to start out by trying to evaluate a function. We're given the function f of x equals -3 times x squared plus 2. Order operation says that first thing we are going to do after we substitute is to work through our powers, our exponents, then through our multiplication division, then through our addition subtraction last. So step 1, we are given -2 to plug in. So we're going to take -3 times -2 squared plus 2. So first write that out. Next order operation says we square it first. So -2 times itself, that's what squaring does, is 4. So we now have -3 times 4 plus 2. Order operation says that we next have to multiply before we add, so we get -12 plus 2. And finally, we end up with -10. We're going to do the exact same thing over on here, the other side with 5y. So we're going to have -3 times 5y squared plus 2. We square first, so we first need to figure out how to do that. 5y times itself, 5y times 5y. I'm just going to do that as a side problem here. 5y times 5y. Remembering that 5y is really 5 times y. It's just a big C of multiplication, which means the order we do things doesn't really matter. So let's do the 5 times 5 to get 25, and the y times y to get y squared. We still have the -3 times all of that, plus the 2. And we know that our multiplication comes next. So -3 gets added into this big C of multiplication. So let's multiply our numbers to get -75. And our letters, our variables, stay as they are because there's nothing new there. So it's still y squared, still plus 2. And what's nice about this one is we have unlike terms being added or subtracted, in this case added. So our final answer is -75y squared plus 2. And we are moving on. As we head into parent functions, we are looking at the function y equals x to the third power, also stated as y equals x cubed, which is why I know it's a cubic function. Now let's create a table or chart for this, starting with our x's. I like to use the common values -2 through 2. And then actually do the math to get the y values if you haven't memorized these. So I like to start at the positive end, so the bottom of the table. 2 to the third power, 2 times 2 times 2 is 8. So I'm down here at 8. 1 times 1 is 1 times another 1 is 1. 0 times anything is 0. -1 times -1 is +1 times another -1 is -1. Same thing for the 2's. -2 times -2 is 4 times -2 is -8. So I'm going to take all these points here and graph them. Now the 8's actually go off the chart by a little bit, but we'll still mark those. And when we do that, we get a fairly ziggy line here. We put little arrows on the top and bottom to remind us that this does in fact keep going beyond the points we have. Not perfect, but that's a rough approximation. Describing that graph without numbers, I usually like to say kind of an S-shaped. You could call it maybe like a steep bent line. There's a lot of ways you could describe a cubic function. Something to the effect that it implies there's that curve or bend in there. And that's it for our graphing a function. So we switch on to inverse functions. Now there's 3 main inverse functions we've looked at: the square root, the cube root, and the log function. And they each invert something. So square root inverts a square function. Cube root inverts a cube function. And here we're given something a little different, the exponential. So that's the exponential. And the inverse of the exponential is the log function. So this one's a tough one. Y equals log little 2 base 2 of x. And the log function works the same way the exponential function does, except x and y are swapped. So how do you know what x and y values to use for an inverse function? You swap them from the original function. So in this case, it'd be swapping them from the exponential. So if we normally go -2 to 2 in the x's, we're going to do it in the y's this time. -2, -1, 0, 1, and 2. We're going to build our table backwards. And if we remember when we did exponentials, 2 to the x power, 2 to the power of whatever x is, 2 to the second power is 2 times 2, that's 4. 2 to the 1 power just means the number 2 itself. 2 to the 0, anything to the 0 power, when the exponent is 0, is actually 1. Negative exponents take the result that we got from the positive exponents, but they put 1 over it. They put it at the bottom of the fraction. So it's going to be 1 over for both of these. And 1 over 2 to the 1 is just a 2 on the bottom. 1 over 2 to the 2 is a 4 on the bottom. The other pattern that happens with exponentials is you keep dividing by 2, or in this case, whatever your base is. But to go from 4 to 2, divided by 2, you get to 1. Divided by 2, you get to a half. Divided by 2, you get to a fourth. And that pattern would continue as well. Now, because it's the inverse of the exponential, it's the log function, we flip x and y. So I already wrote it that way. So I have my x's here and my y's over here. So let's graph these points. The point 1/4, -2 is going to be down here. The point over a half, down 1. We've got over 1 up 0. We've got 2 over 1 up, and then 4 over 2 up. And what you start to see is a trend that looks something like this. It's our log function. If you want to get real fancy, we have a what's called an asymptote, a dashed line here that none shall cross ever. And that goes straight up and down right there. And there we go. Moving on to our domain and range with this function down here, a nice challenging one. We are looking at what's called the 1 over x function, or reciprocal function. So this is the 1 over x, the reciprocal. Reciprocal means flip the fraction. So 1 over x. And then we look at this graph. The domain is what x's are possible. So as we look at the graph, we have things going to the left forever and ever. We have things going to the right forever and ever, which would make me want to say it is -infinity on the farthest left of my domain, my x range, my domain, to +infinity. Now, this is one of those really unusual functions where we have one exception to that, and that is we have an asymptote right here up the middle, meaning that every x is possible from -infinity all the way to infinity except one, except x equals 0. So I'm just going to write in parentheses here, x not 0. This is the only function that you're going to deal with that has an exception in the x in the domain. So just letting you know that for this one rare function, that's a thing. What is the range? The range is the possible y's. The lowest possible y goes down forever, -infinity, and goes up forever, +infinity. So the y's are going to be the exact same thing, -infinity to +infinity. And they have that exact same problem because we have an asymptote going this way. We can never be 0. So we can put y is not 0. Not equals sign right there is an equal sign through a slash through it. It's a way of saying not equal to. So this is one of those rare exceptions. I don't think that any other function we deal with is going to have those problems. Now, is this a function? The way that we can tell if this is a function is if we draw a straight up and down, a vertical line anywhere, will it only go through one point? So I just drew one through that, and it only went through one point. Drew it through here, it only went through one point. Drew it through here, only went through one point. And in fact, you can draw this anywhere, and for every x, there's exactly one y. There's no place where we get multiple y. So it is a function. Yes, it is. And the reason is that for any vertical line, we go through only one point. So that's what you need to know with that. For any vertical line, we go through only one point. And that's it for the first page.